Hey everyone, welcome to our presentation. My name's Jackson, along with my teammates Brett, JT, Sam, and Garrett. And we're going to be walking through the clip video search program that we built over the last few weeks. Next slide. Before we get started, I'd like to run us through what we'll be talking about today. First, we'll be looking at the background of clip as well as its architecture. Next, we're going to explore some methods that we utilize to enhance computational time, including frame consolidation. Next, we're going to dive into some applications and examples across a variety of disciplines. And in addition to that, we'll mention some common issues that surface when trying to apply our program to those examples. And then finally, we're going to wrap it up with some recommendations for some future work, as well as recommendations to enhance our existing program. At this time, I'll turn it over to Brett to talk about the clip background.
Thanks, Jackson. So CLIP was developed by OpenAI in 2021, and it's a model that connects language and images. It was trained on over 400 million image and text pairs. It encodes both the image and the text, and that's how it's able to find the closest matches between the lists of images or the list of text and find the closest match between those. It also has what's called zero-shot capabilities, which means that it can predict on classes that it's never seen before, and that comes from the text and the image embeddings. A little bit on the architecture of CLIP. CLIP uses the basic transformer model, and it's for the text. And its transformer model has 63 million parameters, 12 layers, it's 512 wide, and it uses 8 attention heads. And it takes the text input, and then it outputs an encoded vector that represents the text phrase. For its images, text uses Vision Transformer, which was created in 2020 with a slight modification. It adds a normalization layer, and the Vision Transformer allows it to encode an image the same way that it encodes the text, and it produces an encoded vector, which it's then able to compare the two using cosine similarity, and it will choose the closest combinations of cosine similarity that it gets from the text and images. And now I'll pass it off to Garrett to talk about our work with frame consolidation.
So our goal in this project was to parse through videos to find matching frames to search queries based on those text encoded images that Brett was just talking about. With this, it gets very computationally expensive, takes a long time to go through every image. So one of our goals of this project was to increase the computational speed of searching the videos. And so initially CLIP just searches through every single frame and encodes it, and then it'll go through and match cosine similarity for every frame with your search term. So what we decided to do was try to find a process that would segment different frames and create one matrix that you could run cosine similarity on for those, and you would choose the best cluster, and from that cluster you would choose the best image. While we tried a bunch of algorithms to get this to work, including summing all of the matrices, averaging matrices, taking the difference from the average and summing that number, none of them were really able to work any better than just getting lucky to find the right clump that had the right image you were searching for. So in future work, we're going to look into finding a better algorithm that can cluster without losing the important factors of each image. And so now that we've talked a little bit about how we were trying to improve the speed of this, we do want to talk a little bit about the results that we achieved, and JT is going to start us off with that.
Thanks, Garrett. So yeah, looking at some of the results and applications that we looked at, first doing a Netflix episode search, you might recognize these scenes here from The Office. We went over some YouTube videos off of The Office pranks, and we wanted to see if we could find a match for something that might be a little bit obscure. So in this case, we searched for a desk in wrapping paper for the top picture, and then on the bottom for a man holding a bag of seeds, trying to get these very specific scenes, and it actually came back with the exact scenes in some words that you might not have expected to be able to search for. And the execution time, as we can see, was about 1 minute each for about 15-minute videos, and the frames extracted were 269. There were some issues that we went in through the applications. Namely, we were searching for the stapler in the Jello prank, and that one had trouble. That is also like a small image, but it could get the stapler if we searched for the stapler alone, but it had trouble with some specific pranks. So it's kind of sometimes a trial and error, which is an issue. And now I'm going to hand it off to Sam to talk about other applications.
Yeah, so here's an example where we looked at a football highlight video of Ray Lewis. So the search query here was strong collision, and we were just trying to extract those frames where big hits occurred, which would help doctors kind of diagnose which players are more susceptible to concussion trauma compared to others. And this was about a 20-minute long video, and it extracted a relatively large number of frames because this was a highlight video, so there was a lot of hits in it. And the execution time was 9 minutes. Next slide. Yeah, so then I tried searching the same video with a separate query, which was big hit, which is kind of a more domain-specific terminology. And this query did a lot worse than the previous query, which was strong collision. So this kind of speaks to just the problem of search query engineering, where you kind of have to search videos for the right search terms in order to get accurate results. Next slide. So this is another example with traffic camera footage, and the search query here was taxi, and you can see it was really accurate in extracting those frames that actually included taxis. And so there's applications here in government, which would be kind of traffic optimization, and criminal justice when searching traffic camera footage for a specific type of car, which I'll get into in the next slide here. So this search query was white sedan, and this was only a 1:30 long video, and this was the only white sedan that appeared. So it was really accurate in extracting the frame that actually included a white sedan. So now I'll pass it off to Jackson to give us another example.
Thanks, Sam. So the final use case that we explored was interrogation footage. In this example, we're looking at police body cam footage of Chris Watts, who was convicted of murdering his family. And the search query that we used here was nervous man. And so in the scenes that you can see on the left side of the screen, it picked out the exact moments where he was exhibiting signs of nervousness, where in the top image there, we see him grasping his head with both of his hands as they watch the neighbor's surveillance footage of him backing his truck into his garage at 4 a.m. And then again in the closet where he's desperately trying to convince the detective that he had nothing, or he had no idea where his wife and kids were at that exact moment. So this definitely has some strong applications in criminal psychology and enabling police departments and investigators to pinpoint exact signs or specific behaviors for further analysis by a psychology professional. Next slide. Here's another example with Stephanie Lazarus. And the search query here was deceptive woman. And this one is interesting because at these exact moments in the interrogation, she was feigning a lack of knowledge or inability to recall certain details that when we watch a true crime psychologist perspective on this video, we were able to verify the accuracy by getting their opinion, and these were the moments that they highlighted in the interrogation footage as being moments where the suspect was being highly deceptive. Again, it has a similar use case where police departments and investigators can look at, search for specific behaviors, and then based on the results of the query and the images and the moments in the video that it shows up in, be able to further analyze those moments. However, this one did have some issues where, similar to what Sam and JT were mentioning, it required some query engineering in order to extract the exact right results. For example, the first criterion that we searched for was deceptive behaviors or signs of deceptive behavior. And these captured moments where the suspect was out of picture, where she would perhaps sit forward or lean forward out of camera view, when those necessarily weren't the deceptive moments or the most deceptive moments of this interrogation. Next slide, please. With all that being said and all the applications we discussed, some ideas and recommendations for future work. As Garrett mentioned, we're going to continue to look at frame consolidation, exploring different methods and algorithms in order to not only enhance computational time, but also maintain the accuracy that we have when we utilize all the frames. Additionally, similar to what we mentioned throughout discussing the examples, query engineering. So being able to pair domain-specific applications such as signs of nervous behavior or signs of deceptive behavior with a search query converter that could perhaps generalize the query and make it more applicable and accurate, in a smaller context. So that's something that warrants further consideration as we move forward. At this time, I'd like to open it up for any questions. Thank you for listening.